Hello, welcome to the 2024 John Lyons Lectures. I'm Gernot Heiss, I'm the John Lyons Chair, and if you don't know who John Lyons is, you'll find out in a few minutes. Sorry about the delay. We have got an open house. We had to add more chairs to accommodate everyone, which is a good problem to have, obviously. It's great to see so many people. It's great to see Marion and Liz Lyons. Thank you very much for attending. It's great to see so many familiar faces. There's a lot of alumni from my group who are into operating systems, obviously. It's great to see so much interest. It's great to just see so many people in general. So the John Lyons Lecture is an annual event we're holding at UNSW. It's, I guess, the most high-profile, regular event talk series the School of Computer Science and Engineering is offering. And to give you more detail about the school and what it does, let me introduce our head of school, Professor Haibo Chen.
Thanks, Gernot. Thanks for the introduction. So I would first start off by giving an acknowledgement of country. I would like to acknowledge the Bijikal and Gadigal people that are the traditional custodians of this land. I would also like to pay my respects to the elders, both past and present, and extend that respect to other Aboriginal and Torres Strait Islanders who are present here today. To start off about the School of Computer Science and Engineering, the school has been in existence on its own since January 1st, 1991, and I think there's just a handful of us who were there at that time and are still here on the staff. And I'm proud to say that I'm one of those. I joined the School of Electrical Engineering in 1990. And moved over to the new School of Computer Science and Engineering when it was formed. And what can I say? John Lyons was one of the first that I met in the school. It was a very small school at that time with barely 18 to 20 staff. And Professor John Lyons was one of the senior staff there who was very willing to show me around and show me the ropes, so to say. I learned from him how to write reference letters for students. I'm very proud to say that. He actually gave me a sample that he'd written for somebody else and showed me the ropes. So it was a really fantastic time, a small school growing. Today the school is huge. We have got equivalent of 7,000 equivalent full-time students enrolled mostly in our coursework undergrad and master's coursework programs. We have over 200 PhD students, at any given time between 20 and 30 postdocs, who are all funded by research grants, including Gernot's, but also many others in the school. And we have, again, anywhere between 20 and 40 technical, admin, professional staff who are supporting the functions of the school itself. So we've really grown from a very small number since those days. So John Lyons was very well known even then in the 90s when I came in for his unique take on the teaching of the operating system course. His marked up Unix primer was very famous even then. And since those years, we have had Professor Gernot Heiss, but also a group of others who have taken over the teaching of that course and developing that whole area into a really large, well-established, very impactful research team within the School of Computer Science and Engineering. We will hear more about John Lyons himself through the video which has been created, I think, and will be run right now for us. And I welcome you all to this talk, which is funded by the John Lyons Chair and the John Lyons Fund, which was created by John Lyons admirers from those years who have put together a very large philanthropic fund to fund the chair, as well as activities in the systems and operating systems area in particular, right? So my sincere thanks to the John Lyons Fund and its and the committee which manages that, and thanks also to all the university groups which support activities in this area. Thank you very much. I don't want to say much more. I think the video will tell you quite a lot about John Lyons, and I welcome you to view it right now. Thank you.
Well, I was doing a PhD here in the department between 71 and 75, and John turned up, I think, in 1972, fresh from Bell Labs.
I first met John in 1975 in the 3rd floor tea room of the School of Electrical Engineering. In those days, the Department of Computer Science run by Murray Allen was a very small group of people.
And immediately we struck up a bit of a friendship. The department actually at that time was known as the Department of Electronic Computation. It's a delightful team.
He did a fantastic job of sort of inspiring all the younger students to go and try things.
He influenced the school and most universities around the world in a major way, because he brought with him from Bell Labs a novel operating system. And long story short, all of the computers in the university within a year or two were running Unix, and every university around the world, almost without exception, was using Unix distributions from the University of New South Wales initially. Very proud of that.
John had a massive impact on my life. Because of Unix, I've been able to have a business, a family, and do the things in the world that I wanted to do, because I was able to leverage the information that he taught me and build businesses on that information. John was a great influencer, and hey, I'm nearly 70 and I'm still running businesses based on the information I learnt from John.
All right, so hopefully you have an idea of John Was and why we keep his name in high honor. And now we get to the main game of the evening, the reason we're here for, the John Lyons Distinguished Lecture, which today we have the great honor and pleasure to welcome Professor Haibo Chen from Shanghai Jiaotong University as our speaker, where he is a distinguished professor at Shanghai Jiaotong University. He leads the Parallel and Distributed Systems Lab, which he founded, which has about 50 people, about lots of academic staff and lots of PhD students. And besides that, he actually spends most of his time in industry, and I have no idea how he does that. I got my hands full running a lab of 50 people. So that itself is extremely impressive. It's a really good group. It produces really excellent work in the area of operating systems, distributed systems, and applications of formal methods. And Haibo is one of the people I most respect and admire in the systems area. In particular, I'm a bit biased because he does actual operating systems research rather than just machine learning, which is the flavor of the day. But besides that, he's not just doing OS research, he's doing innovative OS research. He rethinks operating systems design and implementations, does significant new things rather than just incremental addition of existing things, usually Linux, which is what a lot of the work in the space is. I read many of his papers, some as reviewer, some as just target audience. They always impress me by being very well executed, really very carefully and deeply analyzed and evaluated. They're just exemplars of good system work. So I'm very happy that despite his really busy schedule, we found the window where he's got off. There's holidays in China, so he could attend here at UNSW, spend a few days here and give tonight's lectures. He's got plenty of awards and things. He's got many Best Papers awards in the best conferences, SOSP, ASPLOS. As a matter of fact, he was the first Chinese author to get a paper into SOSP, which is the top operating systems conference and generally considered one of the most prestigious venues in all of computer science. He's won a Best Test of Time award from the Distributed Systems and Networks Conference, and he's a fellow of the ACM, a fellow of the IEEE, so these are the two most relevant professional organizations. And he's also, and again, I have no idea how he does it, he's also the chair of the ACM Special Interest Group of Operating Systems. He must live without sleep. But anyway, without further ado, please welcome Haibo Chen for his John Lyons Distinguished Lecture. And apologies, sorry. There is a Slido link for questions. Please use that for posing any questions you have, and we'll hopefully get them answered in the Q&A.
Okay, okay, sure, perfect. Okay, it's really my great honor to be here to give this lecture, and I'm so surprised that God's given me such a high thinking of me. I'm really moved because Gernot is usually my role model of doing operating system research. Okay, so today's talk I try to report our recent lessons and experience with our new operating systems called HarmonyOS Next. And the goal is trying to make a showcase that system research is actually more relevant than ever before. Okay, before my talk, I should mention a little bit about John Lyons. And actually, this is how I started into operating system research. When I was an undergraduate student in computer science, once a day, one of my teachers handed me a book. The book is called Lyons Commentary on Unix 6th edition. And this book, I remember, was quite heavy. And when I first got the book, I was thinking, well, it should took me a long time to read that book. But I found that the time spent on reading the book is really worthy. And this is actually the key leading me to the operating system research and engineering. Okay, let's give applause to John Lyons together. So most of my recent years are spent on smart mobile operating systems. I think everyone is using mobile operating systems, right? So you have to use smartphones. So you have to use smart mobile operating systems. And I think this is very important for our everyday life, especially user experience is a key to everyone to use a smartphone. If you get some lagging, get some junks, and it hurts our experience. Also, this is very important to maximize performance. Nowadays, you see that the smartphone is essentially a heterogeneous computer, right? So you have CPU, you have GPU, you have NPU, you have DSP, and how the operating systems manage these resources and deliver this performance to user is very important. Also, this is very important for ecosystems, right? We need to have run a lot of applications on top of the smart operating systems, mobile operating systems together. And there's a lot of research problems here, and it's still continually evolving and evolve very quickly. Just look at the every year, the phone manufacturers usually deliver new operating system editions with all these kind of new features. So it's mainly driven by hardware evolutions, also the application model development, as well as operating system technology innovations. Okay, but I think there's also some questions or some good conversations from the system community as well. Because we see a lot of operating systems from industry, right? The Windows, the Android, iOS, Linux, Linux we consider from the open source community. So there was a very interesting conversation almost 20 years ago, or actually more than 20 years ago, from Rob Peck. He wrote a very interesting position paper published in HarmonyOS, which basically questions that system research is irrelevant. Actually, at that time, I think there's a lot of new operating systems research doing, but how this operating system research can be directly impact the industry operating system development. It's really a challenging question. So this last position paper raised a lot of attention from the system community. As I think the system committee is unique in itself, that we're trying to make good engagement with the industry. We try to push our technologies to industry, and so that we can make a big impact on the real world. Okay, so in this talk, I try to use a case study to basically trying to answer the question, is operating system research mainly industry dominated? I think this answer should be no. I think we have a good ecosystem between the academia and the industry. So in this talk, I try to make a case that system research is actually more relevant than ever before, given that we have a lot of problems arising every day, and from industry perspective, we really need a lot of helps from the academia community. So I try to make a case study with OpenHarmony and as well as HarmonyOS Next. I currently the technical steering committee chair of OpenHarmony, and I'm also one of the main architecture of HarmonyOS Next. So trying to use my own experience to report that how we can make the academia and the industry have a very good synergy. So the idea is that we could have brave ideas, bring brave ideas in the industry, even if that the ideas seems crazy at the beginning. If we can find a good problem and can define a good problems to address, then we can make it having a big impact in industry. And also, the industry could provide timely problems, right? So doing system research is usually that if we have we can define a good problem, then we have halfway success. And also, the open source and community actually can help accelerate the loop a lot. Okay, so first I'm going to briefly talk a little bit about the operating system trends from both the perspective of academia as well as the industry. Okay, so before I mention about the operating system trend, let's first revisit the first operating system. The first operating system, I want to make a quiz now. Otherwise, I shouldn't do so. The first operating system actually was born in 1956. It's actually, I can remember this year very clearly because this is the year when my mom was get born. Okay, so if we look back to the first operating systems, and also I try to understand why the operating system is called the operating system. why it's not called other systems. If we look at the operating systems before, we didn't have operating systems. We need to have human operators to operating all these kind of switches and handling the input and collecting the output. So this means that we cannot release the operators to have fun and maybe have coffee when the system is running. So the force operating systems could consider as systems that can replace a lot of operators, right? But because it's a system, it's a piece of software, it's always running without need to have a rest. So this is the reason why it's called an operating system, a system that replaces the operators and can continuously running. And since the first operating systems, I think we now on the road to a collected intelligent world. And this could have a lot of impact on our everyday life, including healthcare, the food, the energy, and also for a lot of scenarios, including our living spaces, transportations, and enterprise. And all of these are supported by the increasing number of collections, as well as the general purpose computing powers, and also the AI computing powers. Actually, I tried to avoid mentioning AI, but believe me, this is the last slide, so mention AI. Okay, and also cloud, right? So, and also the renewable energy of global electricity generations is also very important, and also all of this cannot be done with an operating system. So the collected intelligent world actually calls for new operating systems. If we look back on the history of operating systems, starting for the first operating system, whose name is GMNAIO, and we have seen several generations of operating systems, including OS 360, and also Unix, and also the Windows, Linux, iOS, Android. So the question here is that for the collected intelligent world, what would be the new operating system be? I think this is going to bring a huge opportunities for operating system research to redefine the operating systems nowadays and for the future. But before we're doing this, I think we need to have a more clear definition of operating systems. I think like 15 years ago, if you look at operating systems, we basically think that this is just like an operating system kernel plus a very few device drivers and also some libraries and utilities. This is the operating system. But for operating system nowadays, it's actually much more complex, much more full-fledged. It's not only the operating system kernel goes much larger and much more complex than before. If we look back at the Unix v6, it could be, if I remember correctly, it could be like around like 10,000 lines of code or so. It's at that scale. If we look at the Linux kernel nowadays, it's more than 30 millions of lines of code. It's much more complex. But not only the kernel becomes more complex, also the device drivers and also the libraries, the utilities becomes bigger and larger than ever before. And also nowadays the operating system not only contains the kernel and the utilities, but also contains a lot of system services. For example, for the smartphone, you have like a power management services, right, that help you to manage your phone's power consumption so that you can use your phone until the end of the day, right? So you don't have to charge twice per day. And also the application frameworks. This is how we use programs to write the applications. We no longer require students who got a like PhD to write applications. Actually, a high school student, even my kid who is currently just 10 years old, who is still on the primary school. I think he can write an application as well. So thanks to the abstractions provided the application framework. Actually, the good news is my kid just won a crazy idea award from his primary school. He just made like a kind of like stuff that can monitoring when you're riding a bike, right? He designed a helmet with all these kind of sensors, so that you can monitor when he was riding the bike, he won't go when he was hit by something else, it got automatic notification to my phone. So this is very easier, and he can do this with very high-level abstractions like the Scratch, Scratch, Scratch programming, right? It's just for kids. So actually, we have a lot of abstractions that ease programs a lot, and this also creates a lot more programs than ever before. So this also makes operating system much more important than ever before. So the first trend I want to mention is about performance. The performance is still very important, even if that we have the processors much more powerful than ever before. For example, my smartphone I hand actually is much more powerful than supercomputers maybe 20 or 15 years or 30 years ago. But the problem is that on the consumer side, the application is actually consuming much more resource and energy than ever before. So but the bad news is that if we consider like the performance gain from the hardware and also the silicon level, we're actually getting a diminishing return from the hardware side, right? So given the continuing rise of the requirement from application side, so we need to explore more on the from the top side, which is that we need to care about the software design, the algorithms, as well as the hardware architecture. So and also we need to combine all this kind of together to have a software hardware chip as synergies to get more performance than before. And also because we need to embrace the heterogeneous hardware, and the form verifications is very important for aggressive optimizations, because we already have a trade-off between the performance and the safety. So sometimes you want better performance, you have to compromise a little bit on the safety. So yeah, we need to have both. The second trend is the diversified devices capabilities, and also the different forms of devices actually brings a fragmented ecosystem. You just consider, right, how many devices we see now. I have a watch here, I have a smartphone at hand, I have a earphone here. All these kind of devices has an operating system inside, and this creates actually a very fragmented ecosystems. I try to use a paradox of classes in sectors as a metaphor. It's just like if we could see like there with over 5,000 species of mammals and more than 1 million species of insects, and if we just like accumulate the number of insects together, it should be one would expect that the class insects to dominate the world in terms of the sheer numbers. However, it's actually the mammal, right, that exert greater influence. So why is this the case? So from this metaphor, we could see that if we have a unified architecture and the collective intelligence, we could like bring more power. So we design an architecture called the UNSW architecture. We try to decompose the operating system into a set of kits, and we could assemble all these kits together so that we can using one single code base to accommodate different devices and the different scenarios. And the third evolution trend is that, sorry, it's still AI. Okay, so AI is transferring the mobile applications from action-oriented to intent-oriented. And I think this is from the user interactions perspective. I think this is true. If we look at the history, look back at the history of the human-computer interaction, we could see that at the very beginning we use like a keyboard, right, to type the characters into the computer. And later we use a touchboard, right? We could just touch the screen, and then we could do a lot of things. And now I think that we eventually switch to voice. In a lot of cases, we try to communicate with the smartphones using the voices, using natural voices, natural language. And also, I think in during some talks, actually, I was taught that I should not move. I usually used to move a little bit around. I think a lot of interactions, human-computer interactions is doing some active capturing of the gestures, right, to understand what I'm doing right now, so I can move freely around the stage. This is also another kind of human-computer interactions. So for this kind of human interactions, and I think one of the main purposes is how do we understand the intent of the users. What the intent is the users. For example, if I put my hands down, this means I probably wanted to move to the next slide, right? So this is my intent. So the operating system need to understand more about the intent of the users. So this might bring a new opportunities for the operating system designers to better understand the user's intent and scheduling the operating system resources to fulfill the requirement of the intent. Okay, so the next part is about the OpenHarmony and the HarmonyOS Next. I won't go very deep about this, but basically I'm going to show you an overview of HarmonyOS and OpenHarmony. So I think a lot of people might heard a little bit about OpenHarmony and HarmonyOS, and I think some may ask me what are the relationship between these two. So OpenHarmony is an open source operating system with it could be like serve as an operating system base. So it's open source. It's just like an apartment without fully without the all these kind of furnitures, right? So the commercial operating system that you have an apartment and you have all these furnitures there. You have your flowers and you have your kitchen, so you have sofa, and then this is basic for you. So OpenHarmony is like your apartment without all these kind of facilities, and HarmonyOS Next is kind of distribution built on top of OpenHarmony with all these kind of furnitures, and you could use it very freely. And also other industries distribution could also build on top of OpenHarmony as well, and they could create their own frameworks and create their own application developers. And also, even for HarmonyOS, like I just mentioned, that we try to accommodate different devices. From this kind of small devices to big devices like a smartphone, or maybe even some bigger ones like a vehicle. So we could make all these kind of devices collect freely to each other. And for OpenHarmony, I just mentioned a little bit that I'm also the technical steering committee for OpenHarmony, and we try to building our operating system foundations and ecosystem for federated all scenarios in a fully connected world. And the philosophy is that we're trying to build a unified ecosystems And so that we also make it open source so that everyone can use the operating systems freely to build their own operating system distributions. And also have a set of architectural characteristics trying to make the operating systems easily customizable, and also building with very easy development tools so that people can build their applications on top of this. Okay, for this the operating systems, we actually tried some brief ideas, which usually believed to be very hard to get adopted, especially for very full-fledged scenarios like smartphone operating systems. One of the key design features is we use microkernel technologies. And we try. I think a lot of people know microkernels, right? Especially we all know SL4 very well, and we use SL4 for doing a lot of research, right? But in our case, is that we're trying to make microkernel designs for more general purpose scenarios. So we revisit the traditional microkernel designs and see how this can fit into a more general purpose scenario. And the result is that we retain the minimality principles, and but we also provide structural support to address performance and compatibility challenges. Especially we wanted to build it into a general purpose operating system that can have a drop-in replacement of Linux, which is a really ecosystem rich operating system. And also we're trying to make it performant, because for the product, from product's perspective, if you sacrifice performance, this means that it won't get adopted. Because even if a lot of people say that they care about the reliability, they care about the security, but in the end, they will put the performance as their first priority, and then comes to the maybe security and reliability, something like that. Okay, so we implement and deployed in massive productions, and we show that it typically with improvement performance of Linux. And the second design features is called One OS Kit for All. I just briefly mentioned. So it's just like a Lego, right? So I travel a lot frequently, and so the only way to make up for my family is that I usually buy some toys and to my kids. And my experience that if I bought some very fixed one, if my bag like a car, or maybe like a kinds of like whatever, yeah. So my kids usually broken it in just 1 hour, and they won't touch it again. So after all these kind of lessons, I decided to buy Lego-based toys to my kids. And because he can build different kinds of like shapes of using the same infrastructures, so he can spend maybe play it with more than 3 months, and even after 3 years, he can bring all these toys back to play again. So inspired by this kind of ideas, we built a code architecture called UNSW. Its basic principle is it's very hard to use one operating system for all these kind of scenarios, but why not we broke it into a set of kits so that we can build a common code base, but assembling all these kind of components together for different scenarios. So this has 3 benefits. One is that we could have a unified architecture across different devices, and this means that the fast time to market and no research and development cost. And the second one is that we could have all these kind of cross-scenario collaboration and intelligence. A second one is that we could have an open and unified ecosystem, because all these kind of operating system distributions are from the same code base. This means much easier to build a unified ecosystem. So this can also come to the third key design features, which is trying to collect all these kind of devices together to form a super device, so that we can smoothly switch our usage from one device to other. So for example, when I was reading something, I need to catch catch the lecture, then I could easily to switch the execution from my phone to the vehicle, so that we can continue. I can continually read or maybe listen to the maybe the audience, so without experience fragment. So we can intelligently collect all these kind of devices together. If we get close, then I just like got all these kind of devices collected without awareness of the users. Okay. So with the OpenHarmony and the HarmonyOS NEXT, and we also tried other research ideas, and we bring all these kind of ideas into the operating systems. The first one is, of course, verification. We know the UNSW is really strong at formal methods, and formal verification especially is interaction with the systems. We're also following this. Actually, my interest into formal verification was inspired by the SSP paper about the formal verification of operating system back to maybe 15 years ago. Yeah. So we also dig a lot of in this space, and but we're trying to narrow down into a set of small problems. The first case I will show you is that how we do verification and optimization of synchronization primitives. So the reason why I do this is the multi-concurrency is everywhere, but it really brings a lot of problems. And especially for operating systems, databases, and even server applications. Also, all these to resort to multiple concurrency to achieve high performance. And but the multiple concurrency is very challenging, and the smarter concurrency is very complex. And when the complexity get out of control, it means that you're going to be in trouble. And sometimes you may have some safety compromise. They either cause crash or cause some disruptions. I'll show you an example by the most experienced programs in this planet, right, from the Linux community. If we look at the Linux lock evolution, the first lock appeared was test and set, has 3 atomics without a fairness guarantee. And in 2008, they introduced the ticket lock. It's simple and spins on single location, and all waiters may have cache misses, but it's a fair lock, right? So because they have it's just like you go to restaurants, you fetch a ticket, then you naturally get served based on your ticket number. But it's caused some scalability problems for multi-core. So in 2015, Linux community introduced Q-spin lock, and it's introduced like 26 atomics, but it brings good fairness as well as good locality, because it's like a queued spin lock. It's based on MCS lock, so that every waiters won't contain on the same cache line. This means that we have very good scalability. But even if for all these kind of most experienced programs in the planet, they also made some mistakes. So if we look at the Linux distributions, we could see that we can see that they introduced weak memory model bugs in Linux version 4.5 and version 0.8, and they got funded after maybe 1 or 2 years, even 3 years later. And the pursuit for performance won't stop here, right? So this means that you're going to introduce more complexity. So now the atomics increased from 26 to 46 atomics. I think it's insane, even for the most experienced programs, to manage all these kind of atomics and get it correct. And we have no idea whether this will get merged or not. The good thing is that it introduced NUMA awareness, right? So that you can run on top of NUMA non-unified memory access machine and get a much better performance. But the problem is that you have risk that the lock might not be correct. So we took a different way towards practical verification. We call it practical verification. The basic idea of formal verification is that showing correctness, right? So we use interactive serial proving, more checking, and to exhaustive all these kind of possible interleavings, all possible encodings, and all possible contexts. But the problem is that it requires high-level expertise required, and also sometimes may have some unrealistic assumptions. For example, we have to simplify the hardware a little bit. I really didn't see a lot of formal verification projects model the underlying memory models as weak memory models, which is really hard. So we took a practical way called practical verification. The goal is not showing correctness. We're trying to increase the confidence. And we try to make it exhaustive as long as it pays off. And sometimes maybe someone asks you, okay, so you do formal verifications, how many bugs did you find? So we do find the bugs, and we do increase confidence. And we try to make it possible for any developer can use it, make it a push button and fully automated. And but in practice, if we have some experts can help, we could define what to check and improve the tool scalability and make the methods more realistic. So there are some cases here. The first case is a project called VSync. Which is a push-button verification and optimization for synchronization primitives on weak memory model. So the basic idea is that we first care about the correctness, right? So we ask the programs to write a correct but not efficient version of the implementation. Then we use the VSync verifier to tell which barriers can be correctly weakened, so that we can find a maximally weakened combination of all these kind of memory models for these atomic operations. So that this means that we could have correct version as well as maximally efficient version. So we can have both. And the result was very promising. And I just mentioned that we also verified the CNA-based Linux Q-spin lock on LKMM. And also, we found that the Linux kernel memory model mismatched the reality. And also, we post a fix to Linux kernel memory models as well. And also, we verify and optimize more than 18 primitives, including 30 cores MCS lock, Linux Q-spin lock, and the master mutex. And also we found bugs in DBDKs, and also I just mentioned that like Harmon's MCS lock as well, and also MariaDB's lock. Actually, these are very subtle. If you look at the MCS lock in DBDK, that even for one single 9 chain, it took around 3 months to get confirmed, get fixed. Okay, we also make it open source. We build a library called libvsync, and which is a high performance verified libraries for synchronization primitives and concurrent data structures. And we actually found a Twitter post from Daniel Vetter, which advised us that never invent your own local primitives because they're really easier to get it wrong. So we try to make it possible for people to invent your own locking primitives with Syncer. Actually, we have done this successfully. We provide aggressive optimization with corrective strategies. And we have all this kind of stuff. We have barrier optimizations with vSyncer, and also some primitives designed, modeled, and checked with TLA plus and TLC. And we could see that we have atomic operations, we have synchronization primitives, have some memory management, and concurrent data structures. And all this kind of embody the brief ideas we published in recent system conferences. And it's get open sourced in OpenHarmony as a sub-project. Okay, the second one is a more complex one. Actually, it's embody some of the lessons I with my students. So I have a student working with me for 6 years, and finally he published 2 papers, one in OSD and one in SSP. It's not too bad, but he's a smart guy. I guess he could publish more. But he only published 2, and the reason is that he worked on very hard problems called concurrent file systems. But file systems are so important because we store all our data into using file systems. When file system crash, we probably were going to lose our data. But it's very hard to get bug-free. But the verification is very desired, but very hard to achieve because the file system is very complex. And especially it has a very powerful but annoying operations called rename. Rename will cause a lot of troubles when you get your file system correct. First, you could have safety properties, right? So when you're doing something in flight, you have a rename to remove a file or maybe rename a file. Then you could easily cause safety issues, for example, function correctness. It also could cause deadlock, right? So it could cause some harms. And this is not impossible. We actually found bugs in Linux as well. So we built a called concurrent relation logic, which is a compilation of a local relay guarantee with a relational specification, and which is supposed to support both safety and liveness properties. For safety, we verify the safety of file system by verifying the linear readability. And to deal with the relay issues, we design a mechanism called help, which is that a thread can logically help other threads to linearize their operations, because there is an external linearizability in the case of a relay. So that we could also handle path interdependency phenomena in file systems. We also verify the liveness, and we use a tactic called dynamic linear definite release by designing a cyclic waitful graph for file systems, so that we can verify the deadlock free by verifying that the waitful graph is always acyclic. So this is the framework, and we have proof in Cork. It's a mechanic the proof. The results shown here is promising, but the work underlining is very huge. So this means that we need to write a lot of infrastructure code, and even for very small file systems, we need to write the proof code maybe at least like 15 times compared to the real C implementation, which is huge. And but the good news is that we found that in many cases we don't need to do the refinement proof. We could use the logic built on top of these file systems to reason about the high-level design. Then we can find the problem, find bugs. So we proved the direction locking schemes of Linux virtual file systems using high-level modeling and verification. And we we've actually covered critical flaws and in Linux virtual file systems. And also, we found that actually Linux virtual file system documentation is not very good. They prove the deadlock-free by contradiction. But from a verification perspective, we should do this in a more forward way instead of by contradiction. And so actually the proof by contradiction didn't find the bug of Linux virtual file system deadlock. Also used this to validate file system safeties in Home kernel as well. Okay, the third example is about rendering architecture optimizations. So I guess a lot of you may experience frame drops, right? So when you're trying to scroll in screen, you got some lagging, right? So you're trying to moving forward, switch to another pace, it's got some delayed. So this is called frame drops. Frame drops are actually very hard to emulate, especially given that the rendering workload it's get fluctuated. And this issue becomes even more challenging because the trend of advanced displays as well as advanced graph features. For example, for the smartphones, I think like 5 years ago, we basically use screens with 16 hertz refresh frequency. And now a lot of smartphones already use 120 hertz refresh frequency. This means that you basically double the workload. And we also see that some keyframes are very heavily loaded and cause frame drops, even with a vsync architecture. I want to notice that this vsync is not the vsync I just mentioned. This is called vertical synchronization, which try to synchronize the screen with the rendering engine. And we found a very interesting case from industry, which inspired our research, is that we found that the frame latency has a power law distribution. We have a lot of frames can be rendered in a very short time, but there are only a few frames that need an excessive long time to get rendered. So this is the inspiration from industry, so that we design a decoupled rendering and display architecture called the DVSync. The DVSync idea is that we should not treat all frames equally. Instead, that for some very lightweighted frame, we could save its time, save the CPU and the GPUs to render some very heavy loaded frames, so that we could use the CPU and the GPUs more efficient and without a frame drop. I think this is also sometimes this could be predictable when you do a scrolling of the screen. Actually, the following rendering process are mostly deterministic. You couldn't know that what will be the following rendering process be, so that we could determine how many workloads the frame how many times the frame rendering will take, and we could use the saved time for the heavy frames. Okay, so the idea was very simple, but also turns to be also very effective. You could see that we, from a real production deployment, we could see that it reduced around 72% of the frame drops in OpenHarmony as well as in LSP. And this is also a major change since the project Butter from Google back to 2012. And this also gives us a new rendering architecture so that we could benefit more workloads, especially more dynamic workloads. Okay, so the last piece of the ideas we explored in this talk is file system optimizations. So this is also, okay, yeah, actually. So this is also inspired by industry. And in a smartphone file systems, we found that actually the read-only or the read-mostly partitions are increasingly larger than ever before. For example, we look at the versions. At the very beginning, there are only 12 megabytes for read-only versions. But in a few years later, we could see that the read-only partition got more than 3 gigabytes. So this is almost 6 times increase. So why we want to set this read-only partitions? Because it's read-only, it's read-mostly. The natural idea is that why won't we compress it, right? So once we have a clearly defined problems, we could have a solution to address this problem. But the direct approach is using our existing compressed file systems, which is called the ScratchFS, which is a state-of-the-art compressed read-only file systems. And we try to use this ScratchFS for system resource. But the result is that the system got even more lagged and even froze for a few seconds when rebooted. The reason is that if we use a very simple design, we could easily have read applications that consumes much more memory because it's a fixed size input compression. The problem is that if you have you use the input size, if you have 1 megabyte, you could compress to maybe 200 kilobytes or maybe 100 kilobytes. So the output could be varied. So this means that it could easily cause, when you read it back, so you read 1 megabyte back, it could decompress into 4 megabytes or 6 megabytes. It could easily cause read application. And also it could consume much more memory. So instead we choose using a kind of fixed size the output compressions, which is much more fits more for our scenarios. So we could significantly reduce read applications and also have a much better compression ratio and also allows in-place decompressions. Also, we choose have a cached I/O and in-place I/Os to even save more memories. Okay, so the results is also quite promising, and we could have the application boot time could be reduced by 10%. 10% is significant for application boot time. And also we could save the system storage consumptions more than 30%. And we also make it open source. And I think the file systems now runs at least 1 billion devices for now. It's freely available at both Linux as well Android as well as OpenHarmony as well. Okay, I just use 4 examples to show you that if we tried some build better collections with industries, get some problems from industry, and also you maybe try some brave ideas in industry, we could have a very good and very promising results. But also we have some lessons here. And the first thing is that ecosystem is very important. So if we do research, we could like bring all this kind of ecosystems, but when you wanted to push this back to the industry, you must care about the ecosystem. So our lessons is that if you want to replace something, be compatible at first, then your native rise is gradually. So being compatible is the crucial first steps for commercial deployment. If you break a lot of things, even if you have much better performance, have much better security, it's very difficult to get adopted. And the second lesson is that doing things in industry is that if we want to push research into industry, is we could use a divide and conquer approach. For example, for the cases of form verification, we try to increase the confidence instead of achieving completeness at the very beginning. And also for form verifications in industry, modeling is a first and also probably the most important step for success. For example, we explored other ideas like we tried to use form verifications to do automated SQL rewriting, and it's very promising. We got a lot of SQL rewriting rules, but the key idea is that we model SQL rewriting as a linear algebra. Linear algebra means that we can using first order logic to verify the equivalence of two SQL statements, which is the key to generate new rules. And also even for the correctness and specification is very hard. Sometimes the correct condition is not that obvious. If sometimes we try to get a very complex and complete specification, which turned out to be infeasible. And sometimes you want to really getting easily adopted, we'd better make it a push button and make it a fully automated lightweight approach. And if you want to really have much more impact, it's more important that we integrate form verification into the development tool chain. For example, when you do laterally build, right? So you found the problem and the second day's morning, tomorrow morning, you could see the result and you could fix why. Okay, so to summarize, I hope I have convinced you a little bit that system research is more relevant than before, even for larger scale industry problems, industry operating systems, we could still try a lot of brave ideas into it and make a big impact. And also we use OpenHarmony and HarmonyOS NEXT as case studies to show that we could really do this. And we believe that with more close collaboration between academia and industry, especially with the help of open source, we could accelerate the process a lot. Okay, I think that's all my talk. Thank you very much.
So, thank you very much, Haibo, for this really amazing talk. It's a, oh, I should use the microphone. This is certainly an extremely impressive portfolio of research. So I'm very much impressed by all the things you've done over the past 10 years. One question I have is, okay, it's quite obvious that industry and academia can benefit from each other a lot, but it's also not clear how to bootstrap this. I mean, bluntly speaking, a lot of academics don't really know how to talk to industry, and a lot of industry people don't really care what's going on in academia. How do you bootstrap?
Okay. Yeah, I think the first step is building trust with each other. Yeah, so I think it starts small. It's from some small project, and we could like show that the research is really make a big impact, make a big contribution to the product. Then we're going to build a trust. Then eventually they are more brave enough to try more crazy ideas.
Okay. Yeah. So please put your questions up on Slido, but I can also, if you raise your hands, I can take questions directly from the audience. Taking one from Slido, question, have you seen major roadblocks caused by heterogeneous hardware? Heterogeneous hardware.
What?
Have you run into any roadblocks posed by heterogeneous hardware? Which I guess you have on phones, etc. That's very heterogeneous hardware, right? So different accelerators, etc. Dedicated cores. What problems does that cause?
Sorry, probably the echo.
So heterogeneous hardware,
yes.
Different processing units. What kind of problems do you run into while trying to deal with that?
Okay. Yeah, sure. we do have a lot of problems with the heterogeneous hardware. I think one thing I show you one example is that, okay, so forgive me, I'm going to mention a little bit about the AI as well, because the AI workloads really demands heterogeneous hardwares. For example, like if you have some maybe virtual person, so basically require a lot of subtasks. Some tasks requires it's CPU intensive, and if you run large language models, it's memory and bandwidth intensive, and if you do some computer visions, it's kind of like a GPU intensive. And how we orchestrate all these tasks together, top like maybe a phone or maybe a PC, so that we could, we also have other constraints like the power consumptions, right? So we want to run it for a long time. And also we need to care a lot about the performance interference. If we do run some tasks, we want to stack the whole operating systems. So how do we can make it more power efficient, and how we could make it performance interference as small as possible, and how we can satisfy users' runtime deadlines, all these kinds of questions we are facing. Yeah.
Okay, here's another really good question. What is a good way to get into systems work in industry? Do you need to go beyond an undergraduate degree? Is doing postgraduate work the way to go?
Okay.
Give the right answer.
Yeah. Oh, you mean I just make sure I catch the you mean the degree, right? So doing industry. Okay. Yeah. I think it doesn't matter much if you have different degrees, but the reality is that if you want to do more research-oriented or maybe more explorative-oriented work, having a PhD sometimes giving some advantage, because it's easier to build trust with the management layer.
That's a very good point. I think we have a special problem here in Australia, that Australian industry by and large doesn't value PhDs, and I know it's different, very different in other countries. Here's a question that probably came from my group. You mentioned something about OpenHarmony's kernel providing more structural support than SCL4. Could you elaborate on what you mean by that?
OpenHarmony support SCL4? No.
More structural support, I'm not sure what that refers to.
More structured, okay, yeah, okay, sure. Yeah, actually it should be the Harmony kernel. We have a more structured support. I think the first thing is that we make it more full-fledged, and by being compatible with probably some Linux APIs and Linux device drivers. This requires a lot of structuring of the operating system architecture. And the second one is that, for example, we have for example, the isolation classes, different isolation classes, because for real operating system deployment, some code are trustworthy, some code are less trustworthy. So instead of just two previous levels, we introduce a few more isolation classes, so that we can have a better trade-off between performance and security. For example, some in-house code that are more trustworthy, we won't put them into a separate multi-server, into a separate server. So this could save a lot of IPCs. And also we use a kind of a techniques called access token, that for a lot of memory management operations, which actually consumes a lot of cycles as well. So we try to minimize these overheads using a new technique called address token. And also for the, I think multi-static, classic or static multi-server designs code a problem called state double bookkeeping. This causes not only a lot of memory consumptions, but also for state synchronizations. And we're trying to using some co-designed objects among these servers as well. Also for the device drivers, we have called twin drivers, trying to make a trade-off between the compatibility as well as the performance. Okay, so we have a lot more. So if you have interest, please read our OSDF papers. Okay.
Okay, there's another technical question, actually two that are sort of the same. Is HarmonyOS POSIX client compliant? And from the perspective of the application developer, how does the kernel API differ from more traditional Unix-inspired one?
You mean the HarmonyOS?
HarmonyOS or OpenHarmony.
Okay, I guess the question was mentioned about the Harmon kernel as well, right? Actually, so because OpenHarmony it's the operating system I just mentioned that it contains not only the kernel, the device driver, the system services, and also the application frameworks. It's provide a much higher level APIs. And for the Harmon kernel, we designed it to be kind of POSIX compatible as well, but also support also a lot of Linux specified APIs, because this is very important to run some large scale libraries as well as frameworks. So yes, it's kind of compatible to Linux instead of POSIX.
And what emerging technologies do you believe will significantly impact the field of operating systems design or computer systems in general in the future? Emerging technologies.
Multi what?
Emerging technologies.
Multi-emerging. Sorry, I didn't catch it.
Emerging technologies.
Multi-emerging technologies.
Yeah.
Okay. Yeah. Yeah. I think we have like the kinds of techniques that, for example, the AI, the human-computer interactions, all these kind of emergent scenarios requires a lot of the emergent techniques. For example, we also consider about importing AI to operating systems as well. And also the form verifications, I think it's very important to building a high performant but correct systems.
So back from the deep tech to industry relations, a popular question: how can small business and startups benefit from academia? What's the best way to stay up to date with these modern advancements?
Okay. Yeah, and for small and medium business, I think it's much easier to collaborate with academia, because they are very much more flexible than the big companies, right? So actually, I saw a lot of small and medium business. They have have academia professors deeply involved. In some of them even are founders or co-founders of that company, because they are quite much more flexible, and so they are probably much more brave to adopt new technologies. So yeah, I think it should be much easier.
Okay, and there is a popular question that's completely different, on which I think we might finish. I'm thinking about doing exchange to China in systems. Does Xiaotung have any undergraduate OS courses? Are there some taught in English? I'm sure the question to undergrad OS courses is yes, but the question is any taught in English?
Yeah, we do. I'm the teacher for undergraduate operating system courses. So we try to replicate the success of Gala's advanced operating system courses. So we spend a lot of time to teach and engage with students. This is a really good way to recruiting top students to do PhD. And if some of the students are very good, and they could even do research under the undergraduate year, and they could publish SSP or their papers. So yeah, I think this is a very good way to do this. So yeah, and I even wrote a textbook after teaching undergraduate operating and courses for 15 years.
Okay. I think we might leave it at this. This was a really great evening, I think. Amazing presentation, very insightful, very broad, and I think well pitched. So thank you very much, Haibo. And I'll enjoy having you around for a few more days, and then we can have drinks. So let's join me, please, in saying again, thanking our speaker for tonight. Thank you.